Okay, we're back, and we're looking at capacitors. In this case, just pure capacitor circuits. We're ignoring resistance. We're not doing RC circuits in this little how-to video, which makes it, a little bit unrealistic unless we're using superconductors. But these are useful to make sure you understand what capacitors are, how they behave, things like how they work, and what the rules are for series and parallel. How they store charge, etc. And these aren't so bad once you get the hang of them, because they're very much like pure resistor circuits, series and parallel resistors. It's the same thinking that goes into this, the same problem-solving steps. We have pretty much a new version of Ohm's Law. If you want to think of it that way, it's kind of like the Ohm's Law for capacitors, Q equals CV. We can use that over and over again for the entire circuit, for individual capacitors within the circuit. And that's how we find the stored charge. So the big difference between the capacitor and resistor circuits, we're looking at currents, moving charges. Whereas in capacitors, we're interested in finding out the stored charge, which basically means we're talking static charge. So the steps we use, again, very much like resistors, instead of finding total resistance, we find total capacitance. Instead of finding total current, we can find the total charge being stored. We can, especially if you have multiple parallel sets of capacitors, we can redraw the circuit as a series circuit. That's useful because really what we're looking for is we need to find the voltage differences for each of those parallel sets. And last but not least, once we have the voltages, we can go back to the original circuits and figure out how the charge is split and how they're stored within the parallels. The big things about series and parallel: in series, for capacitors, we have the same charge. Whereas in parallel, the usual, what parallel means is that you have the same voltages across each of the branches. It's probably best just to go and jump right into an actual example. Throw some numbers in here. And we have this set of capacitors. Microfarads is a very common unit that you have for capacitors. So, looking at our steps, first couple things we want to find is the total capacitance and the total charge. Well, for parallel sets, we can just add those together. Okay, so this set on the right over here would be a total of 18 microfarads. We've got the 9 on top, and then this other set down here, we first have to combine the 3 and 6 in series. Well, in series capacitors, we have to do the reciprocal rule. So that bottom branch is going to be a total of 2 microfarads, and then the total would be the 2 and the 4 would yield 6 microfarads. So this is where it's useful to redraw this as a series circuit. So what I'll do is we'll have the 30-volt battery, the 9 microfarads on the top. We've got a total of 18 over on the side, and then we'll have 6 down here. Okay, so we're just redrawing it. Now we can treat these as individual capacitors. We have series. We actually have to go ahead and do the reciprocal rule again. We have 1 over 9 and 1 over 6 and 1 over 18. Let's see, that's going to be 2, 3, and 1 all over 18. which means we'll have a total of 3 microfarads. excuse me, we can find the total charge. Since we know we have 3 microfarads total and a 30-volt battery total, we have a total of 90 microcoulombs of charge being stored by this particular circuit. So keep in mind what that means. Okay, how do you interpret this number? Well, they're in series, and so we said our rule is through induction and polarization and all this good stuff, each of these capacitors will end up with this total charge on them in series, and that's when you have an equilibrium condition. So that means down here we're going to have 90 microcoulombs, we're going to have 90 microcoulombs up here, and we're going to have 90 microcoulombs over here. Okay, now that's convenient because now we can go ahead and figure out what the voltage is on each of these. So we'll change color here. Okay, so we can use Q equals CV again. Voltage is now charge divided by capacitance. So we have a total of 10 volts being used up across that 9 microfarads. Down here, on the 6 microfarads, we've got 90 divided by 6, which will be 15 volts. And last but not least, on the right-hand side, we've got 90 divided by 18, which should be 5 volts. Now we can make sure we're correct. We can double check. Those 3 voltages should add up to the 30, which they do. That's Kirchhoff's rule. That's still valid. That's valid for any circuit. We can go back up to the original picture and try to finish this off. Okay, so we already know what's going on the top. Nothing changes for the 9 microfarads. That's got 90 microcoulombs of charge on it. Now for the parallels, that 90 microcoulombs is actually going to split. So maybe we'll start off on the right-hand side. We found that the total voltage difference across that capacitor is 5 volts. Well, that means that each of these capacitors is 5 volts. Okay. And we can go ahead and find the charges on each of those branches. 5 times 10 means we have 50 microcoulombs on that one. 5 times 8 means we have 40 microcoulombs on that branch. Those add up to 90. That's similar to what currents do in parallel. They split, and those charges have to add up to the total, so that checks out. And now we can come down to this final set. And let's see, we said that there's 15 volts. Well, that means we have 15 volts on the top branch. And what I'd like to do is I would consider this bottom branch to be a total of 2 microfarads, which is also at 15 volts. So if we multiply those two together, 15 times a total of 2 microfarads is 30 microcoulombs on the bottom branch. 15 times 4 gives us 60 microcoulombs on the top branch. Those add together up to 90. That's our total. That's cool. That means that we were right. And now how do you interpret the 30 microcoulombs on the bottom branch? Well, in reality, we've got 3 and 6 in series. Well, in series, you have to have the same charge. So you actually have that 30 microcoulombs on each of those capacitors. Okay. That's how it plays out. We're basically done. One other thing that could be asked for, I suppose, when you deal with capacitors is the other thing that they do. Besides storing charge, they store energy. 1/2 QV, which is the same as 1/2 CV squared, etc. And we have all the numbers now for each of these capacitors. We could go through and we could figure out the total energy being stored by each individual one, by the whole circuit, whatever you want to do. So yeah, hopefully this makes a little bit of sense and helps out. It's a lot like doing resistors again. We have the same types of steps, the same thinking that goes into all this. And really the key is just to remember that we have in series the same charge on capacitors, in parallel the same voltage. Basically with this small number of rules you can go through and solve any of these types of problems. So I hope this helps, and until next time, we'll see you later.